taking up the homework. Question number 1, find the displacement, or in other words, the magnitude and direction of the resultant of a cruise ship that travels 20 kilometers north, then 60 kilometers west, 60 degrees south. Include a detailed diagram. Solving this question, we're going to put it in the format of GRFS, given required to find formula and solution. Step 1, establishing what our givens are. So I've decided to logically name the vectors A and B. So the first vector I called A, which seems to make reasonable sense, and the second vector B. And we are looking for the magnitude of the resultant, or the displacement really, and its direction. The first thing we work on is do our best to draw a vector diagram. And the goal is we try to make it as clear as possible. So zooming in, and once again a reminder, the first thing you draw is your compass rose. So our vector A has a magnitude of 20 and it's heading north. But our vector B has a magnitude of 60 and the direction was west 60 degrees south. So again, when you draw that, you got to have your wits about you. We point west first, right? Because it says west first. You point west and then you turn 60 degrees towards the south. So west, 60 degrees towards the south. It's going to look something like that. Now that means this angle here is 60 degrees. That part, again, that is not inside our triangle because the resultant always starts from the tail of your first vector to the head of your second vector. So this 60 degrees lies outside of this triangle. I mean, it's not a big deal to find an angle inside. You just got to remember that we have to, remember how math works. That being said, if this is 60 degrees, this here has to be 30 degrees. And that's again because of complementary angle theorem. Once again, we have enough information to solve this. So we know the magnitude of this side is 60. We know this angle here is 30 degrees. And we know the magnitude of this side is 20. So we have side, angle, side, you guessed it, cosine law. So again, we're using cosine law, but in the vector version. So remember, this magnitude of r squared is the same as side c squared. And the magnitude of vector a squared is just the same as a squared. And the magnitude of vector b squared is just the same as b squared. So we're looking for the magnitude of r, which we can just write simply as r by itself. But I do want this first line with the proper notation because it is most correct. So to isolate for r, we take the square root of both sides. And now we're free to substitute in. The magnitude of a was 20, magnitude of b was 60, times, and then minus 2 times 20, 60, cos of 30 degrees. And we get an interim answer of 43.8354. I do want to point out that our final answer will reflect the 4 sig figs. But for your interim calculation, carry more of the decimal places. And if you can, keep it stored in the memory of your calculator because that will result in less rounding error at the end. So now that we have the magnitude of r, we have to find, ultimately, theta. So we're looking for that angle there. Well, again, theta is outside our triangle. So in order to find theta, we do need to figure out what angle B is going to be. And the reason why is we know that angle B plus theta is equal to 180 degrees. And a reminder, we actually didn't have to do it this way in particular. We could have had our theta over here. So in this case, what I've decided is that I thought we could go south and then turn west. Alternatively, we could have gone west and then scooch south. And if we had done it that way, then our theta would have been this little bit in here. I think that's a little harder to figure out. It's not that much harder really, because to figure out that, we could just take B and subtract 90 from it. It's not that huge of a deal. But again, the reason why I chose it over here, it's kind of less clutter. That's really what it comes down to, is it makes my diagram look less stupid. So obviously, we have to find B first. So let's do that. Now, let's talk about angle B. It's pretty obvious that angle B is likely, very likely to be obtuse. And since angle B is likely to be obtuse, it is really, really, really a good idea to avoid using sine law and just stick with cosine law. Now, we have a pretty good idea And I mean, I think in this question, it looks fairly obvious that angle B is going to be an obtuse angle. But my argument is this. There are some questions where, this resultant is going to be closer to that line there. What I'm saying is just don't risk it with sine law. It just breaks your heart all the time. So the two alternatives is as follows, in my opinion, best practice. 1, just use cosine law. It's direct, get it done. Or 2, find this angle first. So finding angle A, guaranteed that it's not going to be obtuse. There's not a snowball's chance in the dominion of Hades for it to be obtuse. And the reason why is because side A is the smallest side, and therefore no risk. Only angle B has a risk of being obtuse. So of course, if we have to isolate for angle B using cosine law, there's going to be a lot of delicious algebra. And let's take a look at that algebra right now. Okay, so again, it's just cosine law. This is just cosine law. And in this case, we're isolating for side B. And the three sides are side B, A, and R. So since we're looking for angle B, it has to be in this form here, which is the magnitude of B squared is equal to the magnitude of A squared plus the magnitude of R squared minus 2 times the magnitude of A times the magnitude of R, cos of angle B. But as I've mentioned before, I am not a huge fan of negativity. So what I will elect to do is I'm going to bring this whole term to the left-hand side, and I'm going to bring this term to the right-hand side. That means this term here becomes positive, and this term here becomes negative, which is reflected in this line right here. All right, so next, and if you recall, we are doing SAMDEB, and that was, your subtraction and addition, and we just finished that, so that's done now, so we can cancel that out. The next thing that's we got on tap is we are looking for the multiplication / divisions. So this part here, the 2A times R, 2 times the magnitude of A, magnitude of R, those are attached to this function through multiplication. The opposite of multiplication is division. People, I got to be honest, I'm not sure what I like more. This kind of ambery orange or the purple. I'll switch it up. All right. Next, we need to get rid of the cos. Well, the opposite of cos is cos inverse or arc cos. And remember, we have to take the arc cos of everything, both sides there. And apparently, when I made my note, I stuttered because I wrote the same equation twice. Okay, so we don't need that line there. And I love how Microsoft Word just randomly likes to bold things. So I'll have to fix that next, I guess. Well, anyway, we substitute the values in. And in this case, we can't get away from it. We have to use the magnitude of R. There's just no other option. And we do that, we get 136.8 degrees. But that's just B. We need theta. Well, again, to get theta, and let's look at the diagram before we run away. We know that beta plus theta makes 180 degrees. And that's because they are supplementary angles. So theta plus beta, B, angle B, is equal to 180. So to get theta by itself, it's 180 minus 136.8, and we get 43.20 for sig figs. Therefore, R is equal to 44.8 kilometers south, 43.20 degrees towards the west. And let's just make sure we understand why. So trying to get the answer and the diagram at the same time. And as a reminder, when you kind of sketch it out, we start from our starting point, which is the tail of A, and we point south first, right? It's in south. And then we rotate 43.20 degrees to the west. So south, 43.2 degrees to the west. So all right, that one's reasonably straightforward, fairly easy. But again, you have to have a very good diagram. The second question, however, is legitimately pure evil. That's right. I am a creature of pure malevolence to give you such a wretched question. And the reason why is because we have to add 3 vectors that are A, not collinear, and B, are not playing nicely. All of them are at some weird angle. None of them line up on the X or the Y axis. That may not seem like a big deal when you're at this stage of the question, just writing this down. But when you realize the nightmare mathematics that this generates, we're all not going to have a good time. Well, I'm going to have a good time because I actually know an easier way to do this. Spoiler alert, but let's enjoy a little bit of the suffering first. All right, so solving this question using our current tools available to us. Spoiler alert, it's terrible in every way. And here's the reason why. We can only work at the moment with triangles. The problem is that these three vectors, when combined, do not make a triangle. So we have to do it in parts, and that is kind of a nightmare. So let me show you what the nightmare looks like. So here's our vector equation. Innocent enough. R is equal to vector A plus vector B plus vector C. Yeah, this is what that ends up looking like. So now here's the disgusting nightmare geometry that you got to do. All right, so we first have to start off with our vector A. So I'm actually going to color code it. I'll just do the first two vectors in blue. So our vector A was, I believe, zoom over here, 1 kilometer north 30 degrees west. Okay, so we start off with that. So we start off with north 30 degrees towards the west. There's our vector A. Okay, cool. But that's the 30 degrees right in there. I'm going to zoom in a little bit. That's 30 degrees. Okay, now vector B, I believe, is 2 kilometers west 20 degrees south. So west 20 degrees south. Okay, so far, so good. But it's this tiny little bit there that's 20 degrees. All right, so now what we have to do is we have to calculate an interim resultant, which I decided to call R1. Okay, so this is why the question is so awful. Because if you make a mistake here, you literally have to start the question over from scratch. And that is unpleasant. So here is our vector, our resultant 1, our interim resultant, calling it R1. Now, I have gone through all the math for you here. So realistically, I'm sure many of you started this question and then promptly were like, yeah, no. Because you probably got a little overwhelmed right at the stage here. So first of all, you have to find these two internal angles. Well, this gamma here is 30 degrees because of the Z pattern. So there's a little Z action right there. See, there's the Z. And then alpha over here, that's going to be 70 degrees because if this is 20 and the total angle here is 90, the remainder's got to be 70 degrees. All right, so that part's 70 degrees, which makes this angle in here 100 degrees. Fun stuff, eh? Okay, so we have side, angle, side. So we have to use cosine law to find our R1. And that's doing all of this. So going through all this math, and there we go, there's the justifications for the angles right here. We get 2.4 kilometers. That's just for our interim. And again, if you make a mistake here, at this stage right here, everything else after this is going to be wrong, which means you'll have to redo it from scratch. It really is quite awful. Okay, but wait, there's more. So, like I said, we do have that value, but now we have to figure out the direction of this vector. Again, this is really just quite terrible. So I'm going to clean up this diagram a little bit to get rid of the stuff that we've already worked with. Okay, so now we have to find this little bit of an angle here. The diagram is so fine that I have to even use a finer tip pen there. And then this is phi, right? So that's this symbol right here. It's a Greek letter. All right, so in order to be able to find phi, we know that phi plus b plus 30 adds up to 90 degrees. So we have to find b first, which means that we have to use sine law or cosine law to do that. In this case, I decided to use sine law because this question's already difficult enough as it is. And there's no chance of b being obtuse because this was already 100 degrees there. So b's totally fine. There's no way it's going to be obtuse. Okay, so using sine law, we find that to be 55.1. So then phi, to get phi, you have to do 90 minus b minus 30, and that's 4.9 degrees. Awesome. Awesome. 4.9 degrees. Sweet. What do we do with that? Well, let me tell you. So here's how things get pretty terrible. Now we're going to do the second triangle. And the second triangle is going to be this one here. I'm just going to highlight it like this. So that is our resultant 1 plus vector C. Okay. And then we get our actual resultant, which is this vector here. Let's thicken that up a bit. Now our R1, if you recall, that was our interim vector. So now here's the thing. We know the length of this side. We know the length of that side because that was given. And this one was scooched down here, 2.4. But we need an angle inside this triangle, inside this green and red triangle. Okay, humans of profound awesomeness. That means we have to borrow some information from the last triangle in order to solve this. And what information is that? Well, that is that angle right there, that phi, because we have a Z pattern, a little Z pattern there, which makes this angle also equal to that phi. And we know this tiny little bit here is 10 degrees. So since we have that amount, which is 4.9, so that little section right there is 4.9, that's 10, and this whole angle in here is 90 degrees. So in order to find angle R, we have to recognize that theta, wrong, try that again, that angle R plus 10 degrees plus phi is equal to 90 degrees. So to find R, we have to subtract this phi and that 10 degrees away from 90, which is what I did over here. So we find angle R is approximately equal to 75.1 degrees with a significant amount of rounding error. But as you see, this question is pretty terrible and it's just going to get worse. All right, so now let's clean this up a little bit and talk about the next approach. So we've got this side, we got this angle, we got this side, and that means none other than cosine law to find the magnitude of R, which we did over here, finding the magnitude of R. So again, remember, this is just cosine law. It doesn't matter that I don't have the same letters that you're used to, like A, B, and C. Just R is one side, C is the other side, and R1 is our ridiculous interim resultant, which probably has error in it, rounding error at least. Anyway, so continuing on with this disgusting mathematics, isolating for R, we get 2.70 kilometers. Awesome. But wait, there's more. So much more. That's just the magnitude. We also have to find the angle. Let's go back to our terrible diagram. And we're back. Let's clean this up. So now, humans of profound awesomeness, we have to find this angle theta. In order to find theta, there's a couple of ways we could do it. One, we definitely need to find our angle C. Not a big deal. We're going to use sine law to do that. But to find it, one of two ways we could do it. We could find this angle in here, this little section. You know what? I'm going to use a different color because this is just getting worse. We'll use blue to represent your sadness. So to find that angle there, that's going to be angle C minus phi. And then, of course, this whole angle here is 90 degrees. So we take 90 degrees minus all of that, and that'll give us our theta. Or we could recognize that all of this adds up to 180. So theta plus angle C plus angle B plus 30 degrees is equal to 180 degrees. And that's what I did there. So we found theta to be 49 degrees to a significant amount of rounding error. And that is, of course, after we found angle C, as I mentioned, having to use sine law. I kind of brushed over that part. So you still had to do that first. So this is the finding angle C part. And then over there is finding your theta. Good times. And then in conclusion, you can get the final result, which is our resultant is equal to 2.70 kilometers south, 49 degrees west. And let's go back to our diagram over there. And I really love how OneNote leaves these artifacts sometimes. It's a totally robust piece of software. So again, as a reminder, that's the south part. And then we scooch 49 degrees west. Pretty fun, eh? That was pretty delicious. So I know that many of you are currently contemplating dropping it, the course at the moment. I assure you that there is a much more intelligent way to solve these problems because this is terrible. Sad face. Poorly drawn. More tears. But in any case, the next video will be featuring something called the component method, which is a far superior method to this terrible method that is just fraught with potential error. So coming up next, the component method, that will be your salvation because this is not the way to solve these more complex questions. Until then, wipe those tears.